A family has 2 children. 2 kids. One of them is a girl. Find the probability that the other is a girl. So to be kind of consistent with our labeling, to use good labeling practices, let's say that knowing that one of them is a girl, that's event A, and both being girls. All right. Oh, and I should have written this. Yeah, find probably that the other is a girl. Or really, I should say that both are girls. It's a better way of phrasing it. We're going to call that event B. So there's a couple ways to view this. I'm usually a fan of what I typically refer to as the reduced sample space method. So knowing that one of them is a girl, our reduced sample space is either that, and I'm gonna write this as omega A, so it's the sample space for event A for sure having already occurred, is, well, we either had a boy then a girl, or a girl then a boy, or a girl then a girl. But we definitely didn't have a boy then a boy, because we know that one of the kids is a girl. And then so then we can say, well, based on these being the only options, the probability that both kids are girls, given that we know for sure at least one of them is a girl, well, there's one way out of the total 3 ways of getting that. Or you can do it more formulaically. Where we use the entire sample space, essentially. In this case, it's not that much more work because the entire sample space, there's just one thing that was missing, right? We have boy, girl, girl, boy, girl, girl, boy, boy. And if I want to find the probability of both children being girls, given that one of them is a girl, that's going to be the probability of B and A divided by the probability of A. The probability of B and A that one child is a girl and that both children are girls is, well, there's only one way you get both of those things happening. Both of the children are girls. So the probability of B and A is 1/4. Probability of having 2 kids that are girls, 1 out of 4. But then the probability of having at least one girl, not exactly one, right? This doesn't say what exactly one child is a girl. It says one is a girl. And so when we read it that way, we're saying, well, you could have 1 girl or you could have 2. I know it's the language there is kind of maybe a little misleading, but we know we're trying to see at least 2 because, or at least 1 because we're looking for there being 2. So there's 1, 2, 3 out of 4 ways that can happen, which is going to be the same, 1/3. So either way you want to view it, it's fine. I generally tend to prefer to try and think of it this way because it just feels easier. But you should do it feels easier for you. Yeah.
Why do we end up having like 4 options? I've been kind of confused in how come like GB isn't the same as BG.
Well, if we take it, so what we're saying here is we're writing the children in the order that they were birthed. So you have an oldest girl, youngest boy, youngest girl. So yeah, so it's weird because like we're kind of thinking about how order doesn't matter, but we're still kind of writing the different ways of doing it because that's how we have to consider it. And actually that really leads well into the next question, which is now let's say it's a slightly different situation, which you might accidentally think is the same until you are more careful about it. So the next example, another family also has 2 children. Kids. You run into them at the store and you meet their child who says she is the oldest daughter or their oldest kid. So we know that their oldest child is a daughter. Oldest child is a girl. Now we want to know what's the probability that both kids are girls. And even though it feels like it could be the same question, we have a different amount of information. Now, if we do it the reduced sample space way, and again, it's good to label your things. So the oldest one being a girl, which I've sadly written in 2 pieces here, right? That's event A. And both being girls, that's event B. So now our reduced sample space well, there aren't 3 things anymore. We don't get boy, girl in this reduced sample space. Our reduced sample space here is just girl, boy, and girl, girl. Those are the only things that can happen if you know the oldest child is a girl. And so then the probability that both children are girls out of these 2 possibilities, well, it's going to be 1/2. There's one option that gives you what you want out of the 2 total options that you have. Or you could do it the other way. You could use the formula. Our entire sample space is still what it was before. It's boy, girl, girl, boy, girl, girl, boy, boy. And now the probability of B given A is the probability of B and A divided by the probability of A. B and A, okay. Oldest kid's a girl and both kids are girls. How many ways can that happen? How many of these have the oldest child being a girl and both children being girls? Just one. So the probability of getting both children being girls is 1 out of 4. Whereas the probability of A, if the oldest child is a girl, well, there's exactly 2 ways that can happen. So the probability of B is going to be 2 out of 4. And again, we see that no matter which way you do it, you still should get the same answer of 1/2. So kind of weird, right? If you know that one kid is a girl and you don't know anything else, then the probability of the other kid is a girl is 1 out of 3. But if you know that one kid is a girl and you know that's the oldest kid, or you know that's if you know basically if you know their birthplace, then that reduces the probability of the other one be, or actually it increases. Sorry, it increases it changes the probability of the other one being a girl, knowing that they are either the oldest or the youngest. This second example here is an example of what we call independence, which I imagine he talked about in class today. Okay, great. So in this second example, events A and B are independent. Here's the way I think of this. The very general kind of way of intuitively knowing this is that knowing that one event has happened doesn't change the probability of the other event happening. So I'll point out that event B, do I like that event B here? Sorry, 1 second here. I feel like I've written something weird. Oh, that's right. Okay. Oh. Yeah, I guess my phrasing is not good here. Sorry, I have to think about this for 1 second here. I feel like I've written this kind of poorly. Yeah, that's not great. Yeah. My phrasing is not good for independence here. That's a bummer. I don't love that though. I'm not sorry. I'm starting something working out in my head that just feels so. So here's the problem that I'm encountering, which I'll tell you. So what I wanted to say, this is where the phrasing here actually matters, I guess. If I phrase this differently, I'm getting the same thing, but it's a different event. So if I phrase this as instead as the second child is a girl, I know that feels like the same information, but it's asking about a lesser kind of thing. it would still work out the same here, right? Our reduced sample space would still be GBGG. Our probability would still be 1/2 here, and over here, our B intersect A would still be just 1/4, right? We want girl for the first child and girl for the second child. None of the other ones have that, and our P of A would still be 2/4. The difference is if we write it this way, and again, I apologize for writing it the wrong way. You're able to kind of consider that second event and just think about what its probability is without worrying about the first one. So here's what I want to say, and we'll do another example of this that might make it a little more clear what's going on here. The probability of B given A is 1/2. Or in other words, knowing that the first child is a girl, the probability the second child is a girl is 1/2. But if you hadn't known the first kid was a girl, you would still know that the probability the second child was a girl was 1/2. Which means that A and B are independent, because knowing that A has happened didn't change the probability of B happening. And that's the real key thing to kind of zone in on here, is that knowing that A has happened doesn't affect the probability of B happening, or vice versa. But usually reading it one way makes more sense than the other way. So intuitively, knowing event A has occurred does not affect the probability of B. Yeah. Excellent question. So they're very different things. Let's talk about them. So independence versus mutually exclusive. I would also point out that another word for mutually exclusive, not inclusive, is disjoint or non-overlapping. And let's do this with some examples. So here's my first example. Let's say that, yeah, we'll go back to this example here. Let's say that we're going to draw one card from a deck, and we want to know what is the probability that we drew a heart given that we know it's a 7. And my claim to you all is that these two events are independent. Knowing it's a 7 or not knowing it's a 7 isn't going to change the probability of getting a heart. Let's take a look and see. So what's the probability of getting a heart? And let's give these things some names. Let's say that drawing a heart we'll call event A. Drawing a 7 is event B. So let me just ask, first of all, what's the probability of drawing a heart? 13 out of 52. Or reduced down to 1/4. Which makes sense, right? Because literally a quarter of the cards in the deck are hearts. Okay, let's find the probability of A given B. And then we do this in either way. We can either use the reduced sample space. So using the reduced sample space, well, knowing it's a 7, how many cards are 7s? 4. There's a 7 of hearts, a 7 of spades, 7 of diamonds, and a 7 of clubs. Okay, knowing that our card is one of these 4 cards, what's the probability that it's a heart? 1 out of 4. Or you can do it the other way. You can use the entire sample space and use the formula and say, okay, great. The probability of A given B is going to be the probability of A and B, that the card is a heart and a 7. There's only one of those, divided by the probability of B. The card's a 7. So the probability of being a 7 and a heart is 1 out of 52. The probability of being a 7 is 4 out of 52. And oh yeah, that exactly gives you the same value. So either way you calculate this conditional probability, it's going to be 1/4. And furthermore, the conditional probability is equal to the non-conditional probability, meaning that these two events are independent. Knowing that the card was a 7 didn't change the probability of whether or not we drew a heart. So A and B are independent because the probability of A given B is equal to the probability of A. There's probably two other equivalent ways of phrasing independence formulaically, but this is the way I usually think about it. Probability of A given some other thing is the same as the probability of just A on its own. I will also point out that these two events, A and B, are not mutually exclusive. Mutual exclusivity is specifically that if one event happening means the other one cannot happen. So let me ask you all, if the card is a 7, is it not allowed to be a heart? No, it can definitely be a heart. There is one card in the overlap. So I would point out A and B are not mutually exclusive because the intersection of A and B is not empty. It is not equal to the empty set, which I prefer to write like this, but you could write it with the Greek letter phi if you want to, with this like the 0 with the slash through it. But I like this notation. Right? There's something in that set, specifically A intersect B is the set containing the 7 of hearts. Furthermore, if two events are mutually exclusive, they're explicitly not independent. You can't basically, so I'm going to say something I think is funny. Mutual exclusivity and independence are mutually exclusive. You can have one or the other and never both. Here's why. If two events are mutually exclusive, in fact, let's just say it. So let's say that, and we're gonna make up, yeah, we can use real events. Let's say drawing a heart and drawing, so let's say A is drawing a king and B is drawing a 2. Can you draw a card that's a king and a 2? Definitely not. So the probability of A and B is 0. Or if you prefer, the intersection of A and B is the empty set. So now let me ask you, what's the probability of A? What's the probability of drawing a king? How many kings are there? How many cards are there? Okay. Which is 1 out of 13. All right. What's the probability of A given B? Knowing that I drew a 2, what's the probability of getting a king? 0. Because it's the probability of the intersection, and the intersection has a 0 probability divided by the probability of B. That's 0 divided by, we don't really care, but it is, 4 out of 13, 4 out of 52. So this is why mutually exclusive events can never be independent, because the probability of one of them given the other one is always going to be 0. And whereas the probability of one of them on their own is typically not 0. I will point out, technically, there's a stupid case where one of the events has a 0 probability, and so they can be mutually exclusive and independent, but it's real dumb. No one should ask you about that. So that's why. So you don't have to be either, right? You don't have to be mutually exclusive. You don't have to be independent. But if you're one of them, you definitely cannot be the other one, and vice versa. So just as a reminder, so mutually exclusive means there's no overlap. Intersection is 0. So is empty. A intersect B is the empty set. or equally phrased, the probability of A intersect B is 0. Whereas independence, you can test for in one of 3 equivalent ways. You can either check to see, does the probability of A given B equal the probability of A? Really, the next thing we write down is the same thing, just switching the order. Or you can also check, does the probability of B given A equal the probability of B? Or the other way, which is a little bit different, but not really, does the probability of A intersect B equal the probability of A times the probability of B? These are all the same condition, just written in a different way. So if you can show that one of these things is true, all of them are true. Or if you can show that one of these things is not true, then all of them are not true. So to test for independence, you test to see if one of these is true. If it's true, then the events are independent. If it's not true, then the events are not independent. Or you could say dependent, I suppose, if you want to use a more concise language. Let's see if I have another good example here. So a lot of the times when we're dealing with probability questions, we assume that events are independent. And that assumption means that if we're trying to find the probability of like this thing happening and this thing happening and this thing happening and this thing happening, means we can just multiply all the probabilities together, because the probability of A intersect B is equal to the probability of A times probability of B if A and B are independent. In case you're curious where this is coming from, it's really coming from the fact that this formula here is really, well, the probability of A given B is really just the probability of A and B divided by the probability of B. And if it's actually equal to the probability of A, if you multiply both sides by the probability of B, you exactly get that formula right there. So that's where that's really coming from. But then we can use that in a question like the following. Maybe. A multiple choice test has 10 questions. Have any of you taken any classes that had multiple choice tests that you did? Yeah, okay. I feel like I remember my econ classes having multiple choice tests. Certainly in your math classes should. But I feel like I've seen someone give a multiple choice in the math class. I was like, really? Okay. Anyway, multiple choice tests have 10 questions, each with 5 possible answers. And we'll say the answers are A, B, C, D. Due to time constraints, we had no time to study. We forgot we enrolled in this class, and then I take the test, and we're just guessing. So find, it's not a very realistic situation, but find the probability of answering all 10 questions correctly by randomly guessing. So we're going to assume that each guess is independent of each other one, right? Getting the first one right or wrong, it's going to have no effect on whether you get the second one right or wrong, and so on and so on and so on. So the probability of getting all 10 correct is the probability of getting the first one correct times the probability of getting the second one correct times all the way to the probability of getting the 9th one correct times the probability of getting the 10th one correct. And each of those probabilities is what? What's the probability of getting the first one right if I just guess? 1 what? 1 out of 5. And that's the same for all of them, right? Each question has a 1/5 chance of guessing it correctly. Or as I would probably prefer to write, 1/5 to the 10th, or actually I'd probably prefer to write 1/5 to the 10th, which is super duper small. It's approximately 1.024 times 10 to the -7th. So 0.0000001024. That probability. Extremely unlikely. What's that? Good question. What's the probability of getting half? I like that question. So the probability of getting, do you want to say exactly 5 correct or at least 5 correct? That's the harder question. Let's do exactly 5 first, and we'll talk about at least. Let's say I know the probability of getting exactly 5 correct. Okay, so the probability of getting 5 correct would be 1/5 times 1/5 times 1/5 times 1/5 times 1/5. What about the other 5 that we get wrong? What's probably getting 1 wrong? 4/5 times 4/5 times 4/5 times 4/5 times 4/5. But the way I just said it is kind of like we got the first 5 right and the last 5 wrong. What if we got like the first 3 right and then the next 4 wrong and then the next 2 right and then the last 1 wrong? Or there's lots of different ways of picking which 5 of these 10 problems we got right. So in addition to needing to multiply by the thing I said before, we also have to choose which of the 10 problems we got to get 5 of right. So how many ways of doing that are there? There's 10, choose 5 ways of picking the 5 questions we're going to get correct. And then we're going to multiply by 1/5 to the 5th for the probability of getting 5 of them right. And then we're going to multiply by 4/5 to the 5th, the probability of getting the other 5 of them wrong. When we calculate that, we 10 choose 5. I'm going to need my calculator here. And by mine, I mean definitely. Because I would actually like to know. I don't just want. So I would say on an exam or one more question, you would leave your answer like this, right? But I actually want to know what the answer is because I think it's interesting. So let's find it. So we're going to do 10, choose 5. We're going to get 252. And then we're going to multiply that by, on top, we're going to get 1 to the 5th, which is 1 times 4 to the 5th, over 5 to the 5th times 5 to the 5th is 5 to the 10th. Let's see, 252 times 4 to the 5th, divided by 5 to the 10th. Okay, you got a 2.5% shot there. I mean, actually 2 6/10%. But that's for getting exactly 5 correct. Here's why I didn't want to jump straight to the question that you said, because if you want to probably getting at least 5 correct, then you have to say, well, the probability that the number correct is bigger than or equal to 5 is kind of tedious to calculate, because it's the probability that the number is equal to 5 plus the probability of 6 plus the probability of 7 plus the probability of 8 plus the probability of 9 plus the probability of 10, which would be that thing we just calculated. So I'm going to write out a couple of things and then you can kind of see the rest. So that's going to be 10 choose 5 times 1/5 to the 5th times 4/5 to the 5th. And then if I want to get 6 right, it's going to be 10 choose 6. I have to pick which 6 I'm going to get right. And then it's going to be 1/5 to the 6th power times 4/5 to the 4th power, plus 10 choose 7 times 1/5 to the 7th times 4/5 to the 3rd, plus all, I think you get the idea now, plus all the way to the last part, which would be what we calculated up here. 10 choose 10, which is 1, times 1/5 to the 10th times 4/5 to the 0th. So you have to calculate those like 6 things and then add them all together, which is a bit much. I'm not going to do that right here. What I am going to answer is a slightly easier question to answer and often one that gets asked, which is, yeah, we'll make it a little more interesting. What's the probability of getting at least 2 questions right? And you might think, James, that feels like more work. You have to do 2 plus 3 plus 4 plus 5. And I say, well, maybe not. I didn't say exactly 2. There's a very important word here. I said at least 2, meaning getting 2 right, or 3 right, or 4 right, or 5 or 6 or 7 or 8 or 9 or 10. But instead of doing all of that, right, what's the probability that I'm gonna just say the number is equal to 2, plus the probability that the number is equal to 3, plus all the way to the probability that the number is equal to 9, or the probability that the number correct is equal to 10. Instead, I can say, well, there's just a couple things missing. Getting 1 right or getting 0 right. So if I instead take the entire probability, which should equal 1, if I subtract off the things that are missing. Sorry, I'm using X because that's very cool. That should be equivalent. Instead of adding up all the things I want, I'm going to take the entire 100% and subtract off the things I don't want. Or in other words, I'm using the complement here. So let's do that. The probability that X is equal to 0, or I should say so I've started using X because it's very typical. We're just saying X is the number correct. Probability of getting 0 correct is 10 choose 0 to get right, times 1/5 to the 0th power, because we got 0 of them right, times 4/5 to the 10th power. That's just going to be 4/5 to the 10th. And then the probability that X is equal to 1 is going to be 10 choose 1 times 1/5 to the 1st times 4/5 to the 9th, which is going to be 10 times 4 to the 9th over 5 to the 10th. These numbers are not going to be nice. Let's figure out what we've got here. Yeah, I'm so 4/5 to the 10th. It might not be too terrible. Okay, that's not so bad. 4/5 to the 10th is approximately 0.107. And then 10 times 4 to the 9th over 5 to the 10th is approximately 0.268. So we add that together. We get approximately 0.376. Sure. Because of rounding. And so then our answer is going to be approximately 0.624. So there is a 62, slightly higher than 62% chance of getting at least 2 questions right. I mean, it's not a very good score, but still, like, if that's what you had to do for whatever reason, then like, great. So this is one use of the events being independent, right? We're able to multiply all these things together because we are assuming that each event, each question being asked is independent of each other question being asked. Cool. Yeah, let's start going. So let's start walking down the base formula path. And I use the word path there kind of intentionally because often it's really nice to draw this using what I call path diagrams or tree diagrams, which I hope he showed you in class. But if he didn't, it's also fine. We'll get there eventually. So maybe not today, though. So look at this first example. A blood test for some disease shows a positive result in 98% of the cases where the disease is present. I want to point out that what I've just written down in words is a conditional probability. Given that someone has the disease, the probability of a positive test is 98% or 0.98. We'll write that down in a minute, but it's always weird with conditional probabilities because like you're reading the thing you're saying that happens is read last, kind of, which is unfortunate. So, and also there's a comma here, and I don't love this phrasing, but this is how it's often phrased. And in 6% of the cases when the disease is not present. Disease is not present. I don't love this because I feel like by the time I've gotten to this part of the sentence, I've forgotten what it's based on. So we're saying we're getting a positive test result in 6% of the cases where the disease is not present. That's what that says there. And then finally, assume the prevalence of the disease, prevalence, I can spell, kind of, is 1 out of 250 people. So first question here is going to be, if we select someone randomly, if we select a random individual, what is the probability they test positive? I'm going to show you a couple ways of doing this because I think it's worth seeing both. So I would always give things names. Yeah, and I'm gonna. So often I would use a plus sign for a positive test and a minus sign for a negative test, but not going to do that here because reasons. Let's say that A is the event of having the disease, and B is the event of testing positive. And then we would say that A complement, the leftovers of A, is not having the disease. And B complement, the leftovers from testing positive, is testing negative. Is your teacher using a C for the complement or a prime? Okay, great. Either notation is widely used, but we should. So this question is asking me to find the probability of B, the probability that someone just tests positive. Let's write down a few of the probabilities that we know. We know some conditional probabilities. We know that given that someone has the disease, the probability of testing positive is 0.98. So in other words, the probability of B given A is 0.98. We also know that given someone doesn't have the disease, they have a 6% chance of testing positive. The probability of testing positive, event B, given that they do not have the disease, is 0.06. Do be careful with those single digit percents, like 6% or 8%. You have to have a 0.06. And often I've seen too many people over the years forget that important zero there and be like 0.6, which is 60%, not 6%. So just be careful about that. And then finally, the other thing that we know is the probability that someone has the disease is 1 out of 250. Which you certainly could change into a decimal. It'd be 0.004. Yeah. Because 1 out of 25 is 4%. So 1 out of 250 is 0.4%, which is 0.004. Cool. So how do we do this? Well, there's a couple ways. I really want to show you the way that's easiest though. So I would actually probably, I would say lots of things. So I want to find the probability of having the disease. Nope, of having a positive test. Read the words, right? I say to myself, read the words. What's the problem? What time is it? I was like, what time is it? You guys can tell me if I went over, right? I mean, by more than a few minutes. Okay. So I like to make a table, not a table, a tree diagram. Where each branch, and a branch can have more than 2 branches, like you could have 3 branches. Each branch kind of represents all possibilities of that one thing happening. So the first branch, I would start with my first branch being the person either has the disease or doesn't. For 2 reasons, really. One of them being just that feels logically the most sensible place to start, but also because we know that the testing positive is based on whether or not they have the disease. So it makes sense for the disease branch to come first and the testing branches to come second. So on this first branch, either someone has the disease with a probability of 1 out of 250, or they don't with a probability of 249 out of 250. But basically you have to have all the possibilities in that branch. Great. So now, on the branch where it's already given that someone has the disease, you can either test positive or test negative. Given that we have the disease, what's the probability of testing positive? 0.98. Right? They told us in the problem, they said a blood test for a disease shows a positive result in 98% of the cases where the disease is present. So given that the disease is present, the probability of testing positive is 0.98. Now, I always write this as B up here, but it's probably technically more correct to write it as like B given A. That's what's really going on here. This is really B given A. Just like this here is really B complement given A. I've never done it that way, but it really is, doing it this way is better, like kind of pedagogically. Okay, so if we know the probability of testing positive, given that we have the disease, is 98%, what's the probability of testing negative, given that we have the disease? Well, all these people have the disease. 98% of them tested positive. And the rest of them, 2% of them tested negative. It has to be the rest. There's only two options. You either test positive, oh, we already know all people that test positive, there's 98% of them, or you test negative. Those are the only two things that can happen. So that's going to be 0.02. And then down here, same deal. If you don't have the disease, you can either test positive given that you didn't have the disease, or test negative given that you didn't have the disease. Oh, can you guys see that? Okay, let me zoom in here a bit, make that a little bit easier to see. So we know that if you didn't have the disease, the probability of testing positive is 0.06. So if 6% of the people that don't have the disease test positive, what percent of the people that don't have the disease test negative? You could also just say the rest. I know, right? It's, let's see, 1 minus 0.06 is 0.94. But we know it's the rest. The nice thing about these trees is that each branching has to add up to 1. This branch, these add up to 1. This branch, these add up to 1. This branch, these add up to 1. Always true. You have to have all the possibilities happening. So now, if I want to find the probability of B having tested positive, I'm just going to add up all the paths that get me to B. So here's one path that gets me to B, having the disease and then having a positive test, given that I have the disease. So I'm going to write that. I'm going to write this actually in the formulaic way, just so you all can see it. This is going to be the probability of having the disease and testing positive. That's this branch right here. I should really say that's this path right here that has these 2 branches in it. Or this other path where I have not having the disease and still testing positive. But really what this amounts to is the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. This is the more formulaic way of doing it that I'm writing out so you can see it, but I would almost never actually write this formula. What I would do is I would say, okay, great, I want to find all the ways to get to B, so it's going to be this times this, because right, to get to B, I need to have the disease and test positive. Notice the emphasis on the word and there. I need to have the disease, and so we multiply test positive. Or I add, I need to not have the disease. Sorry, can you see that? Yeah. And multiply test positive. So this pathway or this pathway, we add those together. This pathway consists of this branch and this branch. We multiply those together. This pathway consists of this branch and this branch, so we can multiply those numbers together. And then if we add these together, we get approximately 0.0638. I will point out that this probability of testing positive is very, very close to the probability of testing positive given that you didn't have the disease. And the reason that's true is because of the prevalence of the disease. It's very unlikely that someone has the disease. So for those small fraction of people that actually have the disease, almost all of them will test positive. But that's just a small number that the majority of the influence of what's driving this result is that almost everybody, right, 249, right, 99.6% of the people don't have the disease. And overall, most of those people, or I should say, word James, yeah. 6%, oh gosh, yeah. Sorry, now my brain, yeah. And we're looking for the ones that test positive, so it's going to be the 6% of that large number of people that are testing positive. Yeah, I feel like I didn't say that very well, but yeah. Yeah. Okay, that's our time. So what I would really like to do, yeah, let's go ahead and say this because we should. So the question I would really like to answer here is, what's the probability of having the disease given that you tested positive? Because that's the real actual thing we do, right? You take a test for something, and if you test positive, you might test again because maybe there's a really high chance of a false negative, right? But maybe you don't. You probably do. So, but that test is kind of telling you, well, usually we believe the test. So let's ask, what's the probability of having the disease? That's event A, given that we tested positive. That's event B. So in other words, what's the probability of A given B? We know the probability of B given A is 98%. The probability B given A, sorry, A given B is not going to be the same. And I know it's 2 o'clock, so I'll wrap this up very quickly. So here's the fast way of doing this. It's our usual formula for conditional probability. Probability of A and B divided by the probability of B. We already know the probability of B. It's literally the thing we just calculated. It's your 1 out of 250 times 0.98 plus 249 out of 250 times 0.06. The probability of A and B is just the branch, the path on this tree that has A and B. So it's just the 1 out of 250 times 0.98. Let's calculate that so you can actually see the number. And I don't have it here, so I'm going to actually have to calculate it. So it's going to be approximately, let's see, 0.98 divided by 250 divided by 0.0638 approximately. That's about, yeah, about 0.0614. Very different than the probability of testing positive given that you have the disease, right? So if you have the disease, there's a 98% chance of testing positive. If you test positive, there isn't a 98% chance you have the disease. There's a 6% chance you have the disease. So very, very different, right? It's actually a really important statistical idea that these conditional probabilities reversed really don't have any, I mean, there's some bearing, but like you can't get one value from the other value. They're really very, very different some of the time. So we'll talk more about, and this is an example of Bayes formula, where you're given some conditional probabilities and asked to find the reverse conditional probability. And this is the formula. I know we didn't write it out formula. We'll do that next time. All right. See you all next week.